Okay, can you hear me? Yes. Yeah, okay. Yeah, so thank you very much, Leah, for inviting me to give a talk on this MSE webinar series, and I'm really happy to be here. So, yeah, I'm gonna share some recent research on my project, which is on sustainable glycerol electrolysis for co-production of hydrogen and value-added chemicals. So before we kickstart, I would like to emphasize the world energy status. So you probably have been hearing this for many times, but it's never too much to see this. So the world's primary energy consumption has been increasing rapidly over the last decades, and it's gonna be projected to be further increasing to 2050. So if you look at these three main energy consumption sectors in the thermal, transportation, and power, you could see most of the power has been energy has been supplied by fossil fuels. Only a very small proportions are made from renewable energy. And as a result of burning fossil fuels, you emit a significant amount of CO2, and that caused the atmosphere CO2 concentration to a record high, which is 440 ppm earlier this year. And this has compared to just half a decade ago, it has been increasing a lot. So we need to develop renewable energies to replace the fossil fuels. But with renewable energy, such as solar power or wind power, you could generate electricity, which could decarbonize the power sector. But for the thermal and transportation sectors, you would need something that could carry the energy while it still would be a clean energy carrier, which brings the topic of today, which is hydrogen. So if you see in the end use of hydrogen, it could be used in many different sectors, like reforming ammonia production, transport, or make methanol, or used as heat. But if you look at where the hydrogen comes from for the hydrogen produced today, they are mainly from, still mainly from fossil fuels, such as natural gas and coal reforming. So this has been dominated the global annual hydrogen production, which is around 70 megaton last year. And as a result, you get the CO2 emission for just the hydrogen production up to 830 megaton per year in 2019. And if you are not have a clue of this number, it actually equals to the annual CO2 emission of UK plus Indonesia. So that is quite a lot. So a clean approach is water electrolysis and hydrogen from renewable resources, such as these two, but it only takes up around 2% because it would require massive electricity, and also the cost is a bottleneck. So in the hydrogen production cost for different technology options projected for 2030, we see the cost in US dollars is reduced compared to what's the cost for today. But compare with the natural gas reforming or coal reforming, electrolysis grade is still quite high, and it's not comparable with them. But what if we could reduce half of the electricity consumption? And then if you compare, they actually have the advantage to take over the hydrogen production of what we need nowadays with our society. So that brings us the concept I'm going to introduce today, which is, we call it biomass electrolysis. So it's actually resembling a water electrolyzer, which you have a proton exchange membrane which separates the cathode and anode. On the anode, you oxidize water into oxygen, where on cathode, you reduce the protons into hydrogen. But the problem with water oxidation is it has a very sluggish kinetics, and it appears at equivalent potential at 1.23, but actually in real life, you need around 2 volts to drive the reaction. But if you replace the water with biomass, because biomass is thermodynamically easier to oxidize, so you actually could reduce the energy requirement at the anode, while you can still produce hydrogen at the cathode. So if you look at this thermodynamics diagram, which shows standard Gibbs-free energy of different feedstocks and also the energy efficiency. So you see the water electrolysis and the solid state electrolysis, it has a Gibbs-free energy around 237 kilojoule per mole, while the energy efficiency is also around 5 kilowatt per hour if you want to make 1 numeric cubic meter hydrogen. Well, for the bio-derived chemicals such as methanol, ethanol, and glycerol, you actually need quite small amounts of energy requirements. And if you see here is the kinetic comparison, the biomass electrolysis is also very very comparable with water electrolysis, while you only need just 1/4 or 1/3 of the energy input. So for my project, I firstly studied the glycerol oxidation, and we gave it a fancy name of Glycerolyser, which, like we said before, it's system that resembles the water electrolysis, that you produce hydrogen at the cathode and the chemicals at the anode. So glycerol, it is a waste byproduct from the biodiesel industry. It itself has very low economic values because there are not many places that needs glycerol. But if you oxidize them into such as glyceric acid or tactonic acid, they actually have many applications in cosmetics, pharmaceutics, and food industry, while the hydrogen produced could be used in electricity grid or the manufacturing industry or in the transportation sector. So the project scope at the moment is to develop an efficient glycerol electrolysis system with non-critical elements to achieve a high hydrogen production and glycerol conversion rates with high selectivity to some value-added chemicals. I always would like to divide that into 4 stages. So the first is to understand the electrochemistry and the glycerol conversion pathways behind this reaction. And then we go to the optimization, which to optimize the reaction conditions, such as the electrolyte concentration, the reaction pH, and at what voltage you're gonna do the reaction. And then from there, we need to replace the currently used platinum catalyst, which is actually a critical element, and we need to preserve this resource before it runs out. So we're gonna replace it by alloying with other transition metals such as nickel. So because nickel, it has a high alloying efficiency, it's active in reforming, and also by alloying with platinum, it could tune the d orbital of platinum and make it more stable during the reaction. And then in the 4th stage, we need to improve the performance as in the conversion rate and selectivity preliminary to the 3-carbon product. So here is simple diagram of my device setup. So in between, this is my reactor, which it could be divided by a membrane. So on the cathodes, there's the hydrogen where it would go to gas chromatography or online mass spectroscopy to analyze how much hydrogen being produced and at what potential. And then in the cathode, in the anode, we link it with high performance liquid chromatography to analyze what and how much of the different products. Essentially, we want to connect with a chemical separation unit to separate the different products, but at the moment, we are not there yet. So yeah, at the beginning, as a proof of concept, we investigated with the commercial platinum carbon catalyst and used acidic condition to understand how the catalyst would affect the reaction pathways of glycerol oxidation. So as we see in the TEM and XRD, the platinum catalyst is mainly in its crystal factor 111 form. And if you see in this diagram, in 111 form, you would oxidize the primary alcohol and the secondary alcohol into either dihydroxyacetone or glyceridahide. But if you mainly have a platinum 100, it would only be able to oxidize the primary OH group, which only forms the glyceridahide. So this is one part you could tune with. And then by analyze the electronic states of the platinum before the reaction and after the reaction, we see during the reaction, the platinum has been actually oxidized. So you see the platinum 4+ peak has evolved. So the ratio of metallic platinum and oxidized platinum can also influence the glycerol oxidation pathways, as it shows here. So in this case, you would have the flexibility to tune the electrocatalyst to get the product you wanted. So here is a typical CV curve of the glycerol oxidation in acid media. So you see there are two oxidation peaks. So one is on the forward scan and one on the reverse scan. So the one on both of them are oxidation peak, but the reverse scan is a subsequent oxidation on a cleaner surface because you have oxidized the poisoning species when you go to a higher voltage. And the ratio of this GAF versus GR is actually tell you how the intermediates have accumulated on your catalyst surface. So the product distribution shows that we have both the primary and secondary alcohol oxidation take place, which is via these two pathways. And if you react for longer time, it tends to lead to overoxidation. So you see, before 1 hour, you still get mainly glyceridahide, but at 8 hours, you have, 5 products detected. And we also want to investigate at which the product selectivity at different potentials. But because in different batch, you would have like different reaction parameters, so it's very hard to trace. So an online sampling test is required for the potential check, which I'm gonna show you in the later slides. So, and then we move to the mass spectroscopy to follow real time of the volatile products produced. So if we see on the anodes, we see we could trace the CO2 production. And if you compare this with the CV profile, you see even though the peak at the reverse scan is huge, there's no CO2 formation on this reverse scan. So it means there's only partial oxidation happening, which they are liquids in the electrolyte. And then the CO2 MSCV is around 0.1 volts delayed than the current peak, which suggests that the carbon-carbon bond breaking comes after the partial oxidation, which presumably through the glycolic or formic acids intermediates. But it would need to be further verified with in situ FTIR. And if you look at the cathode, if we remain the constant voltage at 0.9 volts, we see there's constant hydrogen signal detected, meaning at 0.9 volts, which just half of what's needed for water electrolysis, we could already produce hydrogen. So here is a comparison with different electrolytes. So before we were mainly done in sulfuric acid, and if we done the same experiment with hypochloric acid or QH, we see the CV in the hypochloric acid, it has a slightly higher current density than in sulfuric acid, but also it has a higher potential for the glycerol oxidation, meaning it's harder to oxidize the species. While in alkaline, we see it gives much higher current density, around nearly 90 milliampere per centimeter square, and also a very different CV profile. So this might affect the oxidation products. So the reason why in alkaline it has a higher activity is because you have the presence of OH minus ions, which greatly reduce the activation energy of the first dehydrogenation step. So thereby it would facilitate the glycerol oxidation process. But in the acidic media, it promotes the oxidation of secondary alcohol. So it provides you with some flexibility if you want to selectively produce some products that's only on the secondary alcohol oxidation. So yeah, here is product distribution in hypochloric acid. So we see compared to sulfuric acid, we have much less product yield. And also in the background scan, which do not have the glycerol, we see it's not very stable. So this peak represents platinum oxidation. So you see during the scan, it gets more and more pronounced, meaning that the platinum is less stable in this electrolyte. So we would just skip this. And then to the alkaline conditions, we see the product yield is massive, and as well as the current density. And in this reaction, what we found is we mainly formed these 4 products, meaning that in alkaline conditions, we mainly get the primary oxidation, while the oxidation of secondary alcohol is very much restrained. And also in alkaline condition, because it has a high activity, so it tends to over-oxidize the products. So the selectivity to C3 products is only 36 in this case. So yeah, like I said before, we need to reduce platinum content. So what we did is we alloy it with nickel metal. So this is a simple catalyst reaction. This platinum nickel alloy catalyst is actually well studied for oxygen reduction reaction, but I just take the recipe to see if they work with glycerol. And we support it on carbon black just to give it more conductivity. And you see, I don't have a talent to name my catalysts, so they are named by their initials, which is PNCB, meaning it's platinum nickel on carbon black. So here is some electrochemistry. So we see our self-made catalyst compared to the commercial platinum carbon. Some of them actually have a higher activity, and also if by increasing the nickel content, we have a peak shift towards the negative part, meaning that it's more easier to start the reaction. So this could be because by adding the nickel, you actually increased the lowered the activation energy barrier. So because nickel, it has this reactive hydroxide or oxyco hydroxide that could help trap the OH ions for the oxidation. And then if you look at the peak current versus different scan rates, you see we have totally irreversible system, and it's diffusion controlled process. So this is very predictable, because in our system, the glycerol is electroactive species, while we also have the KOH as the supporting electrolyte. So in this case, the KOH is taking care of the charge transfer, while the glycerol would be mainly around the electrode surface and only need to diffuse at the surface to go through the reactions. So yeah, here is the online sampling, like I said before, that we could actually track at what potential what products has been generated. So we see at all 4 different catalysts, we all seem to first get the glyceric acid, which is no surprise because it's the first one you could get from glycerol. And depending on different catalysts, you then have different compounds. For platinum, you have this hydroxyvolvic acid, and then you have this ketomalonic acid. While in the different nickel contents, sometimes you don't have them. But there's always this peak. It's near the glyceric acid, and it's appearing. And at first, it's not showing in my calibration standards, because for HPLC, you actually need to know what species you have in order to know what they are. And if you look at these reaction pathways, basically all of the species I have calibrated, and none of them fit this peak. So that's a problem when you do some electrosynthesis, but you are not actually a chemist by training, so you don't know what's really going on in your reaction. So what I did is I looked into some literature that's doing some similar things, but with heterogeneous catalysis. So what we see here is some DFT calculation on the platinum. So you see at different reaction coordinates, you get different absorption energy, the dehydrogenation energy, CC double bond, and CO double bond sensation. So that means it's not just in an oxidation process, you not only get carbon hydrogen bond sensation and carbon bond, you can also get some carbon oxygen bond sensation. And then if you look at these pathways where all the possible products that could get from glycerol, there is this lactic acid, which is breaking of the carbon oxygen bond of the primary alcohol group. Then you could get this lactic acid. So what we get from this is dehydrogenation dominates at low potential, but at high potential, you can get both carbon-carbon and carbon-oxygen bond sensation. And also the first step of the dehydrogenation would be the rate determining step on platinum catalysts. Well, if you compare the Gibbs-free energy for different elements like platinum, palladium, gold, and nickel, so you see nickel is actually not very far from platinum. So adding nickel would also help oxidize the product rather than just reduce the platinum content. So with this at hand, we investigated the product distribution at 2 hours. So we see compared to the commercial platinum catalyst, we can actually have a better selectivity because we don't have that many different compounds being produced. And with getting more nickel content, we see the glycolic acid has been reduced, while we have more of this lactic acid going on. So this is the reaction pathway I actually draw for my reaction. So with glycerol being oxidized to glyceric acid, it could either go carbon-hydrogen bond breaking to tactonic acid or hydroprovic acid. And it could also go to the carbon-carbon bond breaking to glycolic acid and formic acid. While when you add more nickel, it seems to be promoting the carbon-oxygen bond breaking to the lactic acid. So that's essentially the conclusion we get by adding more nickel in the catalyst. It would inhibit the carbon-carbon bond breaking tendency and improve the ability for carbon-oxygen bonds. And also by adding more nickel, we have a higher production selectivity achieved because we don't have that many 2 carbon or 1 carbon products produced. So yeah, for a future outlook, so at the moment, I was only look at the glycerol and mainly on the anode side. For future, I would need to also look at the hydrogen side to calculate how much hydrogen I can actually get from the reaction. And later we need to expand the concept from glycerol to other biomass-derived molecules, such as HMF or glucose, or even cellulose or lignin. And then we need some not practical lab experiments, but also some modeling or simulations for process simulation to see what's the energy consumption of my process, and some life cycle assessment and the technical economic assessment to see if this process is actually profitable, and also how much of the environmental impact of this process. And hopefully we would get finally this concept of using biomass as a feedstock, the renewable energy as a driving force to get the hydrogen for different end users, and also the oxidation products for chemical industry. So as a conclusion, we would like to develop this glycerolyzer with high activity and good selectivity for hydrogen and value-added chemical production. By doing that, we found that glycerol oxidation on platinum-based electrocatalyst, it could happen in both acidic and basic conditions, while at potential at 0.9 volts, the hydrogen can already be formed, reduce nearly half of the energy input for hydrogen production via electrolysis. And in acidic conditions, we get the CO2 formation at a higher current density in the anode scan, but it's slightly decayed by at the peak current density. While in alkaline conditions, it would provide you with a higher activity because it have this excess OH ions, but it also tend to over-oxidize in the product. So in this case, you would need to find a balance between high activity and also higher selectivity. And also by alloying with nickel, we can reduce the critical metal loading, while it could also change the catalytic behavior. Like we said before, it could promote the carbon-oxygen bond breaking. And finally, this concept needs to be expanded to other biomass feedstocks. So yeah, that should be it. From there, I would like to acknowledge my supervisor and some of my collaborators, and also the fantastic group of TT-RISI group. So yeah, thank you for your attention.
Thank you very much. So I just wanted to remind everyone that you can put your questions into the Q&A function, but we do actually have questions already in the Q&A function. So did you want me to read them out, or?
Yeah, I think I can read them out. So it's from James. So I have two questions. So one, for your platinum nickel system, is a nickel metallic or oxide or hydroxide? So this, fortunately, we don't really know, because you know, it has been conducted this year, and as you see, it's mainly some electrochemistry and HPLC, which we could do in our lab. So the characterization of the catalyst is not conducted very much this year, but we would need to do some XRD, XPS, and also some TEM to find out what the composition of the catalyst. And then second is, am I correct thinking that DHA is a particularly valuable product from glycerol oxidation? If so, do you have any insight on how to maximize its selective synthesis? Okay, yeah, so it is correct that DHA is a very valuable compound, and there are many reports that demonstrating that you could get a higher selectivity towards DHA. So from my understanding, I think one is you tune if you're using platinum, you tune the crystal effects or the oxidation states to make it more profitable to the DHA, or some people also report it by adding some P block elements such as tin or bismuth, or yeah, those P block elements, it could absorb on your platinum surface, and in that case, it would block the reaction tendency to the glyceraldehyde, and promote more of the reaction towards DHA. But in this case, you need to sacrifice some of the activity to get a selectivity to this product. So yeah, okay. And one from Eva. So what products would you form ideally, and what parameters would be most important to optimize over potential current density, precious metal loading, or Faraday selectivity? So yeah, it's a very good question. Thank you, Ivan. So there are some parameters. I think the potential that you use to oxidize your product is very important. As we see in the online sampling system, when you go beyond a certain point, you would actually over-oxidize your product. So I think potential is important. And the current density, actually it would affect, in my opinion, would affect mainly on the activity rather than on the selectivity, because at this potential, or the electrons are gonna, this certain amount of electrons gonna contribute to a certain product. the precious metal loading is also, in an economic point, it's also important. But I think at the moment, most of the glycerol or alcohol oxidation, if you want to get a high selectivity towards valuable products, for example, in glycerol case, you want some C3 products, it would be essential to use precious metals, because if you use some transition metals such as copper, cobalt, or nickel, you're actually getting most of them as formic acid. Well, formic acid is good, but it's not as valuable as all the such as glyceric acid, those compounds. So that's why we might need to find a way to allowing this transition metal with precious metal to find a way to get a high activity, high selectivity, and also reduce the cost for the catalyst. Ines, have you considered testing different material catalysts like gold in alkaline conditions, for example? Yeah, this actually I did. I didn't show here because it would be like a 1 hour talk maybe, but actually I did with some gold silver alloys and silver palladium and silver platinum. So it could see they have different activities because they have a very different CV profile, and also the product is you have the same products, but the distribution of different products is actually a bit different. So in that case, I think gold would have the tendency to form glyceric acid and glycolic acid, while palladium and the platinum, they both similar, like they would promote the carbon hydrogen bond breaking. So yeah, that would be a very interesting topic, and yeah, we are thinking to do that, but at the moment we are only at the early stage.